The Atlantic Ocean covers roughly a fifth of the entire surface of the planet. Sailors have been crossing it for centuries. Submarines have been running beneath it since the First World War. Transatlantic cables have been lying on its floor since 1866. And yet, right now, as you watch this, the bottom of the Atlantic remains one of the least understood places on Earth. Less than a quarter of the ocean floor has been mapped to a level of detail useful for detecting items such as airplane wreckage or the spires of undersea volcanic vents. The surface of Mars and Venus has been mapped in more resolution than much of Earth's own ocean basin. That number is worth sitting with for a moment. We built rockets, pointed them at other planets, and photographed them from orbit at extraordinary detail. We just couldn't figure out how to do the same for the ground lying beneath the ocean that separates the continents you probably have family on.
And it's not because nothing is down there. The Atlantic floor is a mountain range longer than all the Andes and Rockies combined, a chain of volcanoes still active today, and a place where entire ecosystems operate without a single photon of sunlight. Thriving, complex, and catalogued only in fragments. Every time we send something down there, we find something we didn't expect. Every single time. This is the story of what's actually hiding under the Atlantic. By the end of this, your mental image of the ocean floor will be completely different from what it was when you started. If this kind of science is your thing, where we go past the surface version of the story and into the real, stranger one underneath, subscribe and hit the bell. Every video here is built the same way. Find the actual science, then tell it properly. Before we get to what the Atlantic floor actually looks like, we need to understand just how wrong we were for most of human history.
Because the story of the ocean floor is, in large part, a story of spectacular miscalculation. For most of recorded history, the deep ocean had one dominant theory attached to it: that nothing interesting was down there. The sea had depths, yes, but what lay at the bottom? Almost certainly flat, almost certainly dead. In the common scientific view of the early 19th century, the ocean bottom was thought to be an unchanging, lightless desert, cold, featureless, biologically inert. A place beyond all life, beyond all process, beyond all relevance. This wasn't folk superstition. This was formal scientific consensus, articulated by serious naturalists who had thought carefully about the problem. The argument went roughly like this: no light reaches the deep sea, so no plants can grow. No plants means no food chain. No food chain means no life. As for the geology, with no wind, no waves, no erosion, the deep floor must simply be flat.
A layer of ancient mud, undisturbed since the beginning of time. That was the picture. And for a long time, nobody had a good way to test it. The closest thing to measurement that sailors had was the sounding line, a heavy weight tied to a rope. You drop the weight, you count how much rope runs out, and when it goes slack, you know the weight has hit bottom. In shallow coastal waters, this worked reasonably well. In the middle of the Atlantic, with depths of several miles and ocean currents tugging at the line, it was close to useless. The rope would drift sideways, go slack early, read a false depth. The measurements were rough, and the men doing the measuring knew it. What changed everything was a ship called HMS Challenger, and a voyage that is, by any reasonable measure, one of the strangest and most consequential scientific expeditions in history. No systematic scientific study had been made of the oceans until the Challenger set sail in 1872.
That is a sentence worth rereading. By 1872, humans had built railways across continents, laid telegraph cables across the Atlantic floor, theorized on the origin of species, and mapped most of the dry surface of the planet. Not one serious, organized scientific expedition had ever gone out specifically to study the ocean.
What was in it? What it was made of? How deep it went? What lived in it? HMS Challenger, on loan from the British Royal Navy, staffed with a crew of 237 and a scientific contingent of 6, sailed from Portsmouth, England on December 21, 1872. Most of the ship's guns had been stripped out and replaced with laboratories, deep-sea sampling equipment, and dredging ropes over 7 kilometers long. The scientists on board had no clear idea what they would find. They were operating on the assumption that they would dredge up mud, measure some temperatures, and confirm that the deep ocean was, as expected, quiet and largely empty. They were wrong about almost everything. More than 4,700 new species of marine animals were discovered during the course of the voyage, many found on the sea floor, an environment that scientists had believed too inhospitable to support life. Life was not absent from the deep. Life was everywhere in the deep. Strange, alien, unlike anything seen before, living at pressures that should have crushed it, in cold that should have stopped all chemistry, in darkness that should have made energy impossible. The expedition's multi-volume scientific reports, published in installments from 1880 through to 1895, documented a world nobody had anticipated. John Murray, one of the expedition's senior scientists and co-editor of those reports, summed up the significance of the voyage by calling it the greatest advance in the knowledge of our planet since the celebrated discoveries of the 15th and 16th centuries. He was comparing the Challenger's voyage to Columbus and Vasco da Gama, and he had a point. Among those discoveries was evidence of a rise in the middle of the ocean, a gathering of depth measurements that suggested something large and elevated was running roughly north to south through the center of the Atlantic basin. The Challenger crew couldn't see it clearly. They couldn't explain what it was, but the data was there. A prominence in the middle of the ocean, enormous in scale. Nobody in 1876 could tell you what that ridge was doing there. Nobody understood why the ocean floor was elevated in the middle. The discovery sat in the reports, marveled at and catalogued, for the next 80 years, while the explanation remained just out of reach. The explanation came from sonar, from the Second World War, and from a geologist named Harry Hess, who was, in a very literal sense, stumbling across evidence while doing something else entirely. Hess was a geologist and a United States Navy officer who commanded a transport vessel during the war. He had the forethought to keep the ship's echo-sounding equipment running continuously, even when he wasn't officially mapping anything, even when the Navy didn't require it. The data piled up. Depth profiles, ridge after ridge, valley after valley. Hess filed it all away. He discovered flat-topped underwater volcanoes, which he called guillots, mountains with their summits shaved off, as if they had once poked above the water surface and been eroded by waves, then slowly sunk. Mountains don't just sink. Something larger had to be happening. After the war, efforts to map the ocean floor intensified, thanks in large part to the U.S. Office of Naval Research, and at the Lamont Geological Observatory at Columbia University in New York, a woman named Marie Tharp started doing something nobody had done before. She began translating raw sonar data, thousands of depth pings bounced off the ocean floor, into actual pictures of what the bottom looked like. For much of their collaboration, her colleague Bruce Heezen collected bathymetric data aboard research vessels, while Tharp built the maps at her drafting table in New York, since women were barred from working on ships at the time. It was painstaking work before computers existed. She combed through enormous piles of sonar soundings and plotted measurements by hand. She created profiles stretching west to east across the North Atlantic. Examining the bathymetry of the Mid-Atlantic Ridge, Tharp identified an aligned, V-shaped structure running continuously through the axis of the ridge, a deep valley at the ridge's center. She believed it might be a rift valley, formed by the oceanic surface being pulled apart. The structure was so pronounced that she kept rechecking her calculations. She went to Heisen. His response was not congratulations. He told her it looked too much like continental drift, and at the time, believing in the theory of continental drift was almost a form of scientific heresy. Alfred Wegener had proposed in 1912 that the continents were once joined and had been slowly moving apart. Most geologists, including Heisen, considered the idea mechanically impossible. He made Tharp redo the charts. What changed his mind had nothing to do with her drafting skills, and everything to do with a separate project happening on the table next to hers.
Heisen had hired a recent art school graduate to plot thousands of earthquake epicenters in the Atlantic to help a communications company find the safest places to lay transoceanic cables. The earthquake dots lined up precisely with the rift valley Tharp had found. Exactly where she said the crust was splitting apart. That's exactly where the earthquakes were happening. The seismic data and the topographic data were telling the same story from two completely different directions. And still, the broader scientific establishment resisted. After the Columbia Lab's discovery was made public in 1957, the famous ocean explorer Jacques Cousteau reportedly set out to investigate the claim directly, using his research submersible, skeptical enough to want to see it himself. What his cameras found at the bottom of the North Atlantic matched Tharp's maps precisely. The Rift Valley was exactly where she had placed it. Now Hess had what he needed. He was aware of Tharp's mapping work, and he knew the ridge was seismically active. He also knew that the sediments on either side of the Mid-Atlantic Ridge were geologically young, far younger than the ancient continental rocks on either side. Combining all of it, he proposed that magma from the Earth's mantle wells up along the ridge, forms new rock, and pushes the ocean floor outward in both directions. His colleague, Robert Dietz, working independently, coined the term for this process in 1961, seafloor spreading. The implications were staggering. The Atlantic isn't a static basin, it's a growing one. Europe and the Americas are slowly but surely moving apart. Hess himself called his original paper geopoetry. He knew the idea was beautiful, but wasn't sure the evidence was yet hard enough to present as established fact. That kind of intellectual honesty is rare. He published it anyway, clearly labeled as hypothesis, and spent the rest of his career watching the evidence catch up to the idea. The ocean floor is a conveyor belt. New rock forms at the ridge, spreads outward, and eventually slides back into the earth at the edges of the continents, the whole cycle taking hundreds of millions of years. The Atlantic that exists today didn't exist as a recognizable ocean until about 200 million years ago, when the supercontinent Pangaea cracked open along what is now the Mid-Atlantic Ridge during the early Jurassic. Before that crack existed, the land where Boston sits was physically touching the land where Morocco is today. The ocean isn't ancient geography. It's a relatively recent wound in the surface of the planet, still opening. Seafloor spreading helped establish Wegener's long-dismissed concept of continental drift as scientifically respectable. It triggered a revolution in the earth sciences, and it was built, in no small part, on the careful hand-drawn maps of a woman sitting at a drafting table in New York, who refused to redo her charts a third time. So what does the Atlantic floor actually look like? Not the simplified version, the real architecture of it. Stand mentally on the western coast of Africa at sea level. The ground slopes gently down into the water, the continental shelf, relatively shallow, extending perhaps 100 miles offshore before the bottom drops away sharply. That drop is the continental slope, and it falls quickly to a depth of several miles. At the base of the slope, the terrain levels out into what geologists call the abyssal plains. An abyssal plain is exactly what it sounds like,
Flat seafloor at depth, generally adjacent to a continent, varying in depth only slightly across enormous horizontal distances. These surfaces are the flattest terrain on the face of the Earth, flatter than any desert, flatter than any steppe. The reason for the flatness is sediment. Millions of years of particles raining down from above, filling in all irregularities, smoothing everything to a near-perfect level. The larger plains stretch hundreds of kilometers wide and thousands of kilometers long. In the North Atlantic, the Somme Plain alone covers approximately 900,000 square kilometers, an area larger than Texas and California combined. It sits at a depth of roughly 3.5 miles below the surface, in absolute silence, covered in pale sediment. Rising from the plains, here and there, are seamounts, undersea mountains of volcanic origin, some genuinely enormous. They form from extinct volcanoes that rise abruptly from the sea floor to heights of hundreds to thousands of meters. Some tower higher than the Rocky Mountains, measured from base to summit. They never break the surface, so we don't give them names and put them on tourist maps. Great Meteor Table Mount in the northeast Atlantic stands more than 4,000 meters above the surrounding terrain, with a base diameter of up to 110 kilometers. It's flat on top because millions of years ago, when it was higher, waves eroded its summit level. Then the tectonic plate it sits on cooled and contracted, and the whole mountain slowly sank. These flat-topped sunken mountains, called guyots or table mounts, are actually ancient islands, places where, tens of millions of years ago, something green and alive sat in tropical sunlight. Now they sit in complete darkness, miles below the surface, with fossils of shallow water coral still preserved on top. There are more seamounts on the ocean floor than mountains, hills, and volcanoes on all the continents combined. An estimated 100,000 or more across the world's ocean floors, and fewer than 1% have been surveyed in any detail. Then there are the fracture zones, arguably the most underappreciated features of the ocean floor. Running almost perpendicular to the mid-Atlantic ridge, scored into the ocean floor like parallel cuts, these are regions where sections of ocean floors slide past each other, relieving tension created by seafloor spreading. The faults usually cut across the ridge, nearly at right angles, and the terrain inside them is jagged, exposed, raw. Oceanic crust pulled apart and dragged upward by the grinding of tectonic plates. Near the equator, the Romanche fracture zone divides the mid-Atlantic ridge into its northern and southern sections, dropping to a maximum depth of approximately 7,700 meters, nearly 5 miles, in a narrow, jagged canyon slicing through the middle of the ocean floor. Geologically speaking, it is a fresh wound. It has been that wound for millions of years. Fracture zones aren't just geological features, they're plumbing. Cold water formed at the surface near the South Pole, so dense that it sinks to the very bottom of the ocean, finds its way northward through these fractures like cold air flowing under a door, shaping how the entire ocean circulates. And at the center of all of it, the spine running down the middle of the Atlantic, is the Mid-Atlantic Ridge itself. The ridge runs from approximately 300 kilometers south of the North Pole to near Bouvet Island in the sub-Antarctic, roughly 3 kilometers in height above the surrounding ocean floor, and between 1,000 and 1,500 kilometers wide. Running along its entire length is the Rift Valley Tharp Found, approximately 50 to 75 miles wide, where molten magma from beneath the Earth's crust continuously wells up, cools, and pushes outward from the ridge's flanks. The ridge is spreading at roughly 2.5 centimeters per year, the speed at which your fingernails grow. In a year, you don't notice. Over 200 million years, you end up with an ocean. At the point where the ridge passes through Iceland, it actually breaks the surface. You can stand on it, walk the line where Europe and North America are pulling apart, and watch steam rise from fissures in the rock. Everywhere else, This entire world happens in the dark. 300 distinct segments, each one its own pocket of geology, erupting quietly, spreading slowly, building new ocean floor out of liquid rock in total blackness. Every piece of basalt on the floor of the Atlantic was, at some point, hot liquid rock welling up from the mantle at the ridge. It erupted, cooled, spread outward. If you could follow a piece of that basalt from the moment it erupted at the ridge crest and track it across the ocean floor, after 100 million years or more, it would arrive at the edge of a continent and slide back beneath it, back into the mantle where it started. A geological breath, cycling in slow motion beneath everything. And the ridge doesn't stay quiet for long. Deep beneath the cold surface of the abyssal plain, water has been seeping down through cracks in the crust for millions of years, heating against the magma below and then shooting back up. What it brings with it, what it creates when it returns, is one of the most unexpected discoveries in the entire history of science. The water comes back up black. Not metaphorically black, not merely dark, black. Because it carries a cloud of superheated mineral particles, iron sulfide and zinc sulfide and copper sulfide, billowing out of a chimney of rock at temperatures that should, by any reasonable calculation, turn the surrounding ocean into a boiling cauldron. And yet, the water around the vent isn't boiling. The pressure 2.5 kilometers below the surface is so immense that water cannot physically become steam. It stays liquid at temperatures that would melt lead, and it pours out of cracks in the seafloor in great dark plumes that look, from a distance, like smoke rising from a factory. This is what the crew of the submersible Alvin saw on February 17, 1977, near the Galapagos Rift in the Pacific. The expedition had been sent to investigate persistent temperature anomalies in the water above the spreading center. The seafloor there was warmer than it should have been, by a small but measurable amount. The working theory was mild hydrothermal activity, warm springs, gentle seepage. Nobody expected what they found. Robert Ballard, then a young oceanographer at the Woods Hole Oceanographic Institution, more than a decade before he would become famous for finding the Titanic, was part of that expedition. The first dive found nothing unusual. The second spotted shimmering water rising from the sea floor, the kind of shimmer you see above hot pavement on a summer road. Then the third dive dropped into a place where the temperature gauges spiked, and the cameras started sending back images that the biologists watching from the surface ship simply didn't know how to process. There were clams, enormous clams, 30 centimeters across, with bright white shells, clustered in groups around the warm water vents. There were mussels. There were crabs moving slowly over fields of pale organisms. And rising from the sea floor like a garden from another world, there were tube worms living in white tubes, each one tipped with a red plume waving slowly in the current. The largest were nearly 2 meters long. They looked, in the camera images, like living red flowers growing out of white pipes, covering the sea floor in dense colonies. The biologists on the surface ship stared at the screens, then at each other, then asked the pilot of Alvin to confirm the cameras were functioning correctly. What they were seeing was biologically impossible under the framework governing every understanding of deep ocean life. Every food chain on Earth, as understood in 1977, began with sunlight. Photosynthesis, the conversion of solar energy into chemical energy, was the foundation. Plants capture sunlight and make sugar. Animals eat the plants. Other animals eat those animals. Take away the sunlight, and the whole thing collapses. The deep ocean had life, yes. The Challenger expedition had established that, but it was thought to be entirely dependent on organic material raining down from the sunlit surface waters above. Dead phytoplankton, fecal pellets, the carcasses of surface-dwelling animals drifting down into the dark. a slow, thin, impoverished rain of second-hand energy. What Alvin's cameras were showing was a food chain with nothing to do with sunlight. The tube worms had no mouths, no digestive systems. They had instead a specialized organ called a trophosome, packed with bacteria that metabolized hydrogen sulfide, a toxic gas pouring out of the vents, and converted it into organic compounds through chemosynthesis. Not photosynthesis, chemosynthesis. The sun was irrelevant. The energy came directly from the chemistry of the Earth's interior. The team on the surface was so unprepared for what they found that they had brought no specimen jars appropriate for the organisms they were seeing. They preserved what they could in vodka from the crew's personal supplies. The clams and tube worms that upended biology were pickled in vodka and brought back to Woods Hole. The discovery was not just about unusual organisms. It proved that life could operate entirely outside the solar energy budget. Switch off the sun, and down there, it would make no difference. Equivalent vent fields have since been found along the Mid-Atlantic Ridge, at the Lucky Strike Field, around 1,700 meters depth, at the Rainbow Vent Field, around 2,270 meters depth, where fluids reach 365 degrees Celsius, and at the Lost City Hydrothermal Field, discovered in 2000, which produces highly alkaline fluids driven by the reaction of seawater with exposed mantle rock rather than volcanic heat. Lost City has hosted an active microbial community for at least 120,000 years, making it one of the longest continuously inhabited environments on Earth. 120,000 years of continuous life in the same spot, in complete darkness, at the bottom of the Atlantic. While ice ages came and went, while human civilizations rose and fell, while entire species emerged and went extinct above the waves, this community of microbes and snails and carbonate towers was simply living its ordinary life down there, undisturbed. Away from the vents, the Atlantic Deep has its own population, one of the most varied and strange assemblages of animals anywhere on Earth. The anglerfish is probably the most iconic deep-sea creature, and most people carry a rough mental image of it, a fish with a bioluminescent lure dangling in front of its face, used to attract prey in darkness. That picture is correct, but wildly incomplete. More than 200 species of anglerfish exist, distributed through every deep ocean. The females are the ones with the lure, a modified dorsal fin spine functioning as a fishing rod, tipped with a structure called the esca, which glows through bacterial bioluminescence. The fish doesn't control the light directly. It manages the blood supply to the esca, regulating oxygen available to the bacteria, and through that indirect mechanism, controls the brightness and pattern of the glow. The jaws of a deep-sea anglerfish can open wide enough to swallow prey twice the fish's own body size. The stomach expands to accommodate it. This is what happens when food is scarce and unpredictable. Evolution produces a body that wastes nothing, takes every opportunity, and never passes up a meal. The reproductive biology is stranger still. Males are tiny. In some species, less than a centimeter long. When a male encounters a female, he bites into her skin. His tissues fuse with hers. His circulatory system connects to hers. His eyes degenerate. His internal organs atrophy. Over time, he becomes literally part of her body, providing sperm when she produces eggs, receiving nutrition through her bloodstream, ceasing to exist as an independent organism. Some females have been found with multiple males attached. The male anglerfish ends up as less a fish than a reproductive appendage. I find this genuinely unsettling and fascinating, both at once. Then there are the siphonophores, and these require a moment before the full strangeness lands. A siphonophore looks like a single animal. It is not. It is a colony of individual animals called zooids, each one genetically identical but specialized for a single function. Some are floats filled with gas for buoyancy. Some are swimming bells, contracting rhythmically to propel the colony. Some are feeding individuals with tentacles and stinging cells. Some are reproductive organs. None can survive independently. Together, they form something that behaves like one organism, but is, in reality, a cooperative of hundreds or thousands of beings. A single colonial siphonophore can extend up to 45 meters in length, longer than a blue whale, the largest individual animal ever to have lived on Earth. They drift through the water column, trailing tentacles and curtains, creating a net hundreds of meters wide, invisible in the darkness, covered in nematocysts that paralyze anything that touches them. Siphonophores are also bioluminescent, capable of producing light along the colony's length in coordinated waves. The function of this light is not fully understood. It may communicate within the colony, attract prey, or confuse predators. In the complete dark of the deep ocean, where any photon of light is an event, the siphonophore's glow is simultaneously weapon and signal. The bioluminescence arms race in the deep Atlantic is one of the most complex, ongoing evolutionary competitions on Earth. Predators evolve luminescent lures. Prey evolve sensitivity to detect those lures early. Predators evolve lures that mimic the bioluminescence of prey species' own food, drawing the target into range. Prey evolve sensitivity to longer wavelengths, detecting predators whose light they were supposed to be unable to see. Some deep-sea fish have evolved skin pigments that absorb nearly all light, making them invisible even to bioluminescent illumination. Bioluminescence is estimated to be the most prevalent form of communication in the ocean. Not sound, not chemical signals, light, produced by living things, used for every purpose that language serves above the surface. And then there is the vampire squid, which, despite its name, is neither a vampire nor a squid. Vampiroteuthis infernalis, the full scientific name translates roughly as vampire squid from hell, is classified in its own separate order, distinct from both squid and octopus, an evolutionary relict with no close living relatives. It lives at depths between 600 and 900 meters in the oxygen minimum zone, a region of the water column where dissolved oxygen is so low that most fish and predators cannot survive. The vampire squid lives there precisely because nothing else can. It doesn't hunt. It feeds on marine snow, the continuous fall of dead organic material from above, fecal pellets, dead plankton, shed mucus, bacteria. Two long, sticky filaments collect this material, which is packed into mucus balls for consumption. It lives on death, recycled endlessly from the surface, in a chemical twilight where the ocean barely breathes. When threatened, it inverts its webbed cloak over itself, exposing spines on the inner surface of its arms in a defensive posture. Its eyes, the largest relative to body size of any animal on Earth, are a deep, vivid blue in life. A creature that looks designed by someone with a very dark imagination, living in a zone the ocean has essentially abandoned. Below the animals, below the sediment itself, the Atlantic floor has a different kind of secret, one that runs deeper than any living creature. The floor leaks. Not like a broken pipe, in a slow geological exhalation. Methane, produced deep in the sediment by the breakdown of ancient organic carbon, seeps upward through the seafloor in cold, steady columns. Cold seeps. Seafloor areas where hydrocarbon-rich fluid seepage occurs are found throughout the Atlantic, on both continental margins. Unlike hydrothermal vents, they are not driven by volcanic heat. They are driven by pressure and chemistry, the slow compression of organic material buried in sediment, releasing stored energy in a quiet chemical trickle. At some cold seeps, methane concentration in the sediment is high enough to form methane hydrate, a bizarre material in which methane molecules are physically trapped inside a cage-like lattice of water molecules, forming a solid at deep-sea temperatures and pressures. It looks like dirty white ice. Hold a chunk of it in your hand, and if you scratch the surface with a fingernail, it will begin to burn with a pale blue flame, because the methane it contains is being released and igniting in the air. Flammable ice. Ice worms, Hesioceca methanicola, were discovered in the Gulf of Mexico in 1997, living directly inside methane hydrate deposits. Charles Fisher, a biologist from Penn State University, was part of the research team that documented them. The worms were not merely near the hydrate, they were burrowing into it, creating tunnels through the frozen gas, feeding on the chemosynthetic bacteria living on the hydrate surface. When Fisher's team first examined the images, they couldn't immediately determine whether the pink shapes they were seeing were biological tissue or artifact of the imaging. The organism was making its home in flammable ice, at pressure 300 times atmospheric, in near-freezing water, sustained by gas that would be toxic to most creatures above. The relevance extends beyond Earth. Europa, the moon of Jupiter, covered by a thick shell of ice with a liquid ocean believed to exist beneath it, is one of the strongest candidates in the solar system for extraterrestrial life. Conditions at the floor of Europa's hypothetical ocean are not entirely unlike those at a cold seep on the Atlantic floor. Cold temperatures, high pressure, chemical energy from the interaction of water with rock, and no sunlight whatsoever. Astrobiologists specifically use Atlantic cold seep communities and hydrothermal vent communities as reference points when modeling what life on Europa might look like. The Atlantic floor is, in this sense, a field guide to what might be waiting, cold and patient, and entirely indifferent, in the dark water beneath alien ice. The seafloor doesn't just sit there absorbing what falls on it. Occasionally, it moves. Catastrophically, suddenly, on a scale that reshapes geography and carves structures into the continental margins that dwarf anything erosion produces on dry land. On November 18, 1929, a magnitude 7.2 earthquake struck beneath the Grand Banks, a shallow marine area off the coast of Newfoundland. At approximately 5 in the morning UTC, the earthquake shook loose an enormous mass of water-saturated sediment from the continental slope. This sediment had been accumulating for thousands of years, building up in layers on the edge of the continent, waiting. The sediment didn't just slide, it disaggregated, transformed from solid, layered deposits into a dense, fast-moving slurry so concentrated it was significantly denser than the surrounding seawater. A turbidity current, moving like an underwater avalanche, but faster and farther, following the contours of the seafloor, accelerating down the continental slope, carrying everything in its path. A series of transatlantic telegraph cables lay on the seafloor between Newfoundland and Europe, the communications lifeline of the early 20th century, through which every telegram sent between North America and Europe traveled. And starting shortly after the earthquake, the cables began to snap. Not all at once, one by one. The first failed closest to the epicenter. Then, over the next 13 hours, cables further and further away went dark, in sequence, in exact order of their distance from the slope. Engineers monitoring the cables in Newfoundland and Britain watched the outages appear on their boards and had no framework for what they were seeing. Cable breaks were normally isolated events, a ship's anchor, a fishing net, a localized disturbance. This pattern was something else. The breaks were marching, at measurable speed, away from the earthquake site and across the floor toward Europe. It was Maurice Ewing, a geophysicist at Columbia University's Lamont Geological Observatory, and his colleagues who later analyzed the break times and reconstructed what had happened. Published in 1952, their analysis worked backward from the time of each failure and the known position of each cable on the seafloor to calculate the current's velocity. Close to the slope, the turbidity current was moving at approximately 90 kilometers per hour. It traveled roughly 900 kilometers before finally losing momentum and depositing its load across the abyssal plain. The total volume of sediment displaced was enough to bury lower Manhattan under a layer many stories deep. What this event revealed was that the abyssal plains themselves are largely products of exactly this process. Those vast, impossibly flat surfaces, smoother than any desert, deeper than 3 miles, are flat because turbidity currents have been paving them for millions of years, carrying sediment from the continental margins and spreading it across the deep floor in layers. The flatness is not passive accumulation. It is the result of catastrophic transport events, each triggered by an earthquake or slope failure, each depositing a thin, even layer across the plain. The Grand Banks earthquake also generated a surface tsunami that struck the Buran Peninsula of Newfoundland. 28 people died. The seafloor disturbance had not just snapped cables and reshaped the deep floor. It had displaced enough water to produce a wave that killed people on shore. The ocean floor is not a passive recipient. It acts. It erupts, spreads, leaks methane, collapses, and occasionally sends catastrophic pulses of sediment racing across the abyss in the dark, erasing whatever lay in their path and replacing it with new, flat, featureless plain. And that history is recorded. The sediment lying on the Atlantic floor, deposited gradually from the water column above, or laid down in sudden sheets by turbidity currents, or accumulated around cold seeps and vent fields, is not just geological material. It is an archive. The most complete record of Earth's history available anywhere on the planet, stored in silence in the dark.
Cesare Emiliani, an Italian-American paleooceanographer, spent years in the 1950s and 60s analyzing foraminifera, tiny marine organisms whose calcium carbonate shells accumulate on the sea floor when they die, extracted from sediment cores drilled from the ocean floor. His insight was this: the ratio of different oxygen isotopes in a foraminiferal shell depends on the temperature of the water the organism lived in when it built that shell. Colder water produces a different isotopic signature than warmer water. By measuring the isotopic composition of shells from different levels in a core, each level corresponding to a different period in the past, he could reconstruct the temperature of the surface ocean over hundreds of thousands of years. Not approximately, with genuine precision. What he found upended the accepted understanding of ice ages. The conventional view in the 1950s was that 4 major glacial cycles had occurred in Earth's recent history. The standard model, taught in geology courses, reproduced in textbooks. Emiliani's cores showed something far more complex. Not 4 glacial cycles, but dozens. The climate had oscillated between cold and warm in regular cycles, driven by subtle variations in Earth's orbit around the Sun. The familiar 4 Ice Age model was a crude oversimplification of a much richer, much stranger history. Picture a sediment core pulled from the Atlantic floor. A cylinder of compressed sediment perhaps 30 meters long, representing perhaps 3 million years of continuous deposition. It sits on a table in a laboratory, freshly split in half, and a scientist runs a gloved finger slowly down its length. At the top, recent sediment, grayish, slightly moist. Moving downward, the layers become more compact, subtly different in color. Here, a thin band of rust brown, the chemical signature of increased dust transport from deserts during a dry glacial climate. There, a pale layer of calcareous ooze, the remains of billions of foraminiferal shells from a warm interglacial period. And there, a distinctive dark band, dense, slightly crystalline, volcanic ash. Geochemically fingerprinted, this layer came from a volcanic eruption in Iceland approximately 74,000 years ago. The same layer appears in cores from across the Atlantic, a synchronous dark stripe marking the same moment in time, preserved everywhere. Every mass extinction in the geological record leaves a trace in the sediment. The end Cretaceous event, the asteroid impact 66 million years ago that ended the age of the non-avian dinosaurs, appears in Atlantic sediment cores as an abrupt transition. Below the boundary, a diverse assemblage of Cretaceous microfossils. Above it, almost nothing. Then a slow recovery, new species appearing layer by layer, the ocean ecosystem rebuilding itself over millions of years. You can hold a slice of that moment in your hand, extracted from the Atlantic floor, and look at the precise millimeter where everything changed. Climate scientists use these cores to calibrate models of how Earth's climate responds to changes in greenhouse gas concentrations. They are, in a very real sense, the only long-term experimental record of how the Earth's climate system behaves. Every projection about future climate is informed by what the Atlantic floor has preserved. One detail from this record deserves its own moment. In cores from across the Atlantic, there is a layer corresponding to roughly 56 million years ago, the Paleocene-Eocene thermal maximum, when global temperatures rose by approximately 5 to 8 degrees Celsius in the space of a few thousand years. The warming was accompanied by massive carbon release into the atmosphere, which acidified the deep ocean water and dissolved the shells of carbonate-building organisms. The layer is recognizable in Atlantic cores as a reddish clay, almost devoid of the usual pale foraminifera. A sudden quiet in the record, marking a moment when deep ocean chemistry changed fast enough to leave a visible scar. It happened before. Recovery took hundreds of thousands of years. The sediment layer recording it is a few centimeters thick. A few centimeters and 56 million years of distance. The Atlantic carries records like this by the thousand. Layer after layer of catastrophe and recovery, extinction and radiation, warmth and cold, all stacked in the dark sediment, patient and precise, and completely indifferent to whether anyone ever comes to read them. And yet, even with all of this, the vents, the creatures, the methane ice, the turbidity currents, the sediment archives, there are things on the Atlantic floor that resist clean explanation. Features that appear in sonar data without obvious classification. Biological signals without known sources, acoustic anomalies that propagate through the deep water in ways that don't match the expected physics. The inventory of what lies beneath this ocean is far from complete, and some of what remains uncatalogued doesn't fit neatly into any category we've built so far. There is a recording made in the deep ocean that nobody has fully explained. In 1997, hydrophones maintained by the National Oceanic and Atmospheric Administration, a network of underwater microphones originally deployed during the Cold War to track Soviet submarines, picked up an extraordinarily powerful low-frequency sound from somewhere in the South Pacific. It lasted roughly 1 minute, was loud enough to be detected by sensors separated by thousands of kilometers, and when analysts played it back at higher speed, it had a distinctive upward sweeping quality, almost biological in character. They named it the bloop. The bloop is not the central mystery of the Atlantic, but it is a useful door into the right frame of mind, because the deep ocean is full of signals that arrive without obvious sources, features that appear on sonar without obvious explanations, and patterns of life and geology that don't resolve into clean categories no matter how long you look at them. Working oceanographers who have spent careers on North Atlantic research vessels know this feeling well. Sonar surveys along the eastern flank of the Mid-Atlantic Ridge have returned seafloor profiles that defy available classification. Structures too regular to be random erosion, too large to be biological constructions, the wrong shape for seamounts, the wrong size for vent fields, in the wrong location for turbidite deposits. These features get mapped, noted in cruise reports, with recommendations for follow-up investigation, and then sit in databases that no expedition has since had the resources to pursue.
This is not an unusual story in Atlantic oceanography.
It is a representative one. What the Atlantic floor contains, in addition to everything already described, is a set of geological and biological features that arrived in scientific literature through moments of accidental discovery. Things found when researchers were looking for something else entirely. Things that had no prior category. Things that required entirely new concepts before they could even be named. In 2002, a research team surveying the Gulf of Mexico seafloor found something that initially appeared in sonar data as a field of small volcanic cones. Circular elevated features, roughly symmetrical, clustered in groups. The working hypothesis was low-temperature mud volcanoes, reasonably common on continental margins where gas-charged sediment is squeezed upward by pressure. When the remotely operated vehicle reached the bottom and the cameras resolved the features, the team was looking at something nobody had seen before.
The structures were made of asphalt. Not ancient, fossilized asphalt. Fresh, viscous, dark, and in places still flowing. Natural asphalt seeping from the seafloor in mounds built up over time into rounded hills several meters high. Petroleum that had migrated up through the sediment and solidified on contact with cold seawater, building structures over decades and centuries the way a candle builds a wax formation. Asphalt volcanoes were formally described for the first time from those observations, and equivalent features have since been found along the Atlantic continental margins. A site off the Canary Islands hosts asphalt structures whose full extent and geological history remain incompletely mapped. What makes them scientifically significant beyond novelty is that they host biological communities, polychaete worms, crustaceans, bacterial mats, a food web built on the chemical energy of petroleum hydrocarbons. Asphalt itself, toxic to surface life, becomes substrate and energy source in the deep sea context. Evolution, presented with a new chemical environment, colonizes it. The moment of discovery in 2002 was not dramatic in the cinematic sense. It was a camera image resolving slowly on a research vessel's screen, and a room full of geologists going quiet as the shape on the screen failed to match any template in their experience. One researcher present later described it as recognizing that the category you needed didn't exist yet. That is, in many ways, the defining emotion of deep-sea science. Cold-water coral carbonate mounds tell a different kind of story, one involving timescales that humble any human sense of permanence. Cold-water corals, primarily Lophelia pertusa and related species, grow in deep, cold, entirely dark water. They build calcium carbonate frameworks as they grow, and as old coral dies and new coral grows on top of it, the structure accumulates. Over thousands and tens of thousands of years, the accumulation becomes a mound. Over millions of years, a field of mounds becomes a geological formation. The Porcupine Sea Bight, southwest of Ireland, is one of the most extensively studied cold-water coral environments in the Atlantic. There, at depths between 600 and 1,000 meters, sonar surveys conducted in the 1990s revealed a field of carbonate mounds, some over 300 meters tall, clustered across several thousand square kilometers. The largest of them stand taller than the Chrysler Building, built by animals without eyes, in absolute darkness, 1 millimeter of coral skeleton at a time, over millions of years. Drilling through these mounds produced cores with a continuous biological and chemical record going back several million years. The mounds have been growing and pausing in response to changes in the deep water circulation that brought cold, oxygen-rich, food-bearing currents past their surfaces. When the circulation was strong, the corals grew. When it weakened, they paused. Each mound is, in this sense, a biological recorder of oceanographic history, as faithful and precise as any sediment core, but built from living material rather than fallen particles. Then there are the manganese nodules, which combine geology, economics, and a timeline so slow it makes ordinary geological processes seem rushed. Manganese nodules form on abyssal plains throughout the deep ocean, roughly spherical concretions of manganese, iron, cobalt, nickel, and other metals, ranging in size from a marble to a bowling ball, scattered across the seafloor like a field of dark potatoes. They grow by the extremely slow precipitation of dissolved metals from surrounding seawater onto a nucleus, often a shark tooth, a piece of whalebone, or a volcanic fragment, at a rate of between 1 and 10 millimeters per million years. Per million years. A nodule the size of your fist has been growing uninterrupted for tens of millions of years. Some found on the Atlantic floor are older than the entire hominid lineage. They were already marble-sized before the first upright walking human ancestor existed. When cameras finally reached Atlantic nodule fields in detail, the images showed a seafloor so thoroughly covered with nodules that the underlying sediment was invisible. An irregular pavement of metallic spheres extending to the limits of visibility in every direction. The biodiversity living on and among those nodules in a single square meter exceeded what biologists had expected for an abyssal environment. Animals had organized entire existences around objects that took longer to form than the Atlantic Ocean took to open. These nodule fields are now subjects of serious commercial interest. The metals they contain, cobalt, nickel, rare earth elements, are critical components in battery technology and electronics manufacturing. Multiple companies have applied for deep-sea mining licenses. The ecological consequences alarm marine biologists because the communities living on nodule surfaces, microbial crusts, sponges, soft-bodied invertebrates, have growth rates calibrated to geological time. A disturbance a mining machine creates in an hour could take 1 million years to undo. Every year, somewhere on Earth, a research vessel pulls up a net or a sample collection device from the deep ocean and deposits onto the deck something that no scientist has ever seen before. This is not poetic exaggeration, it is statistical reality. The deep ocean likely contains millions of species, of which perhaps a quarter have been formally described. Every major expedition to unexplored deep-sea environments returns with new species. In 2015, a collaborative expedition working the deep Atlantic margins off Portugal and Morocco brought an ROV to cold water coral habitat at approximately 800 meters depth. The sample arm closed around a small, pale, almost featureless organism attached to a piece of dead coral framework, recorded in passing in sonar surveys, but never physically retrieved. When the sample container surfaced and the team opened it in the shipboard laboratory, they were looking at something bearing no immediate resemblance to any catalogued species. It appeared to be a cnidarian, a member of the phylum including jellyfish, sea anemones, and corals, but its morphology, the arrangement of its tentacles, and the structure of its attachment were unlike any known cnidarian from Atlantic waters. It had spent its entire existence in complete darkness at several hundred meters depth, attached to dead coral skeleton, feeding on whatever drifted past in the current. When the sample container was opened on deck, for the first time in the organism's existence, or in the existence of any of its ancestors back through an unknowable number of generations, it was in daylight. An animal whose entire evolutionary lineage developed in the absence of light suddenly found itself in a container of water under an Atlantic afternoon sky. Whatever that triggered biochemically, it was a moment of contact between two entirely separate worlds that share a planet, but have, until that instant, had nothing to do with each other. The specimen was preserved, transported to a shore laboratory, and formally described 2 years later, adding one entry to a catalog that is still, by any estimate, mostly blank pages.
New species descriptions from Atlantic deep-sea expeditions run at dozens per year, year after year. The Atlantic abyss is not a finished picture. It is barely a sketch. None of what lives in the Atlantic deep operates in isolation from what happens at the surface.
And there is one connection between the deep Atlantic and the surface world that is so consequential and so poorly understood by most people who live with its effects every day that it demands its own space. The Atlantic Meridional Overturning Circulation, the AMOC, is the system of ocean currents that carries warm surface water northward from the tropics toward Europe and returns cold, dense water southward along the deep Atlantic floor. It is one of the primary mechanisms by which heat is distributed across the northern hemisphere, and it is slowing down. The Gulf Stream is part of this system, the warm surface current flowing from the Gulf of Mexico up the eastern coast of North America and then northeast across the Atlantic toward Britain and northwestern Europe. When meteorologists explain why London is warmer than Labrador despite being at a similar latitude, the Gulf Stream is the answer. When farmers in Ireland grow crops impossible in Newfoundland, the Gulf Stream is the reason. When Norwegians fish for species that should not survive that far north, the Gulf Stream is the mechanism. The AMOC works because surface water in the North Atlantic, having traveled north and released its heat to the atmosphere above, becomes cold and salty enough to be denser than the water below. It sinks, rapidly by oceanographic standards, down through the water column to depths of 2 to 3 kilometers, then flows southward along the Atlantic floor back toward the equator and eventually to the Southern Ocean. This sinking is the engine. Take away the sinking, and the whole circulation weakens. Melting ice sheets add cold, fresh water to the North Atlantic surface. Fresh water is less dense than salt water. Less dense water sinks less readily. Less sinking means a weaker engine. A weaker engine means a slower northward flow. And a slower flow means that the heat the AMOC normally carries north, an amount of energy roughly equivalent to 1 million power stations running continuously, stays in the tropics instead of reaching Europe. Researchers at the Potsdam Institute for Climate Impact Research published findings in 2021 suggesting the AMOC is now at its weakest point in over 1,000 years, based on indirect measurements from Atlantic sediment cores and other proxy records. Their analysis, combined with direct current measurements that began in 2004 with the RAPID Array, a series of moorings across the Atlantic at 26 degrees north, the first sustained direct measurement system for the AMOC, shows a circulation that has already weakened and continues to lose strength. What does that actually mean? Not in technical units, in the lived experience of the world. In Dublin, average winter temperatures are kept above freezing partly by heat delivered by the AMOC. Significant weakening would drop winter temperatures across Ireland and Britain by several degrees Celsius, not gradually, but potentially through rapid shifts once certain thresholds are crossed. Growing seasons would shorten. The fish that Norwegian fishing communities have built their economies around for centuries, herring, cod, would be in different places, in different numbers, or possibly both. The rainfall patterns supplying water to Western European agriculture would shift in ways that climate models can predict in broad strokes, but not in precise, actionable detail. None of this is a hypothetical, distant future. The weakening is happening now, measurable in real-time data from the RAPID Array, visible in Atlantic sediment proxy records. The deep Atlantic, through the cold, dense water that forms at the surface and sinks to begin the southward return flow, is a direct participant in the heat economy of a hemisphere. And it is not a stable participant. The deep Atlantic has reorganized multiple times in the geological past. During the last ice age, there were episodes called Danskad-Øsker events, rapid climate swings visible in Greenland ice cores and Atlantic sediment records, during which temperatures in Greenland rose by 10 degrees or more within decades. These were driven by rapid changes in the AMOC.
The Atlantic circulation does not change slowly and linearly. It has tipping points, thresholds past which the system reorganizes rapidly, not gradually. The sediment cores know this. The history of these reorganizations is written in the layers of carbonate and clay at the bottom of the Atlantic, in the isotopic signatures of foraminifera that recorded the temperature and salinity of the water they lived in the chemical markers that tell oceanographers which deep water masses were active and which were absent during each phase of geological time. The deep Atlantic floor is not just a record of past climate. The cold water currently flowing southward through the fracture zones, carrying the chemical signature of the North Atlantic surface it formed from, is part of the circulation engine that determines whether farmland in France stays productive, whether Atlantic fish populations remain viable, whether the cities of northwestern Europe continue to enjoy the anomalously mild climate that allowed their civilizations to develop in the first place. There is a way of seeing the Atlantic floor that only becomes possible once you hold all of this together at once. Not the geology separately from the biology, not the circulation separately from the sediment record, not the vents separately from the cold seeps, or the seamounts separately from the abyssal plains, or the turbidity currents separately from the carbonate mounds. All of it together. One system. The ridge generates new rock and releases heat and chemistry that supports entire communities without sunlight.
Those communities live and die, and their remains settle into the sediment, adding to the archive. The sediment records the climate history of the ocean above it. Every glacial cycle, every volcanic winter, every oceanic anoxic event. And the chemistry of that sediment influences what fluids seep back up through the crust. The fluids support new communities. The communities contribute to the carbon cycle. The carbon cycle influences the deep water formation that drives the AMOC. The AMOC controls the distribution of heat across a hemisphere. The heat determines where rain falls and where it doesn't, which crops grow and which won't, which cities stay temperate and which don't. Follow the thread in either direction, and you end up at the same place. The Atlantic floor is not the bottom of a body of water. It is a dynamic, living, chemically active, geologically violent, biologically rich system connected directly, concretely, through physical mechanisms to the air you breathe, the food you eat, and the temperature of the room you're sitting in right now. The ridge is spreading at the speed of a growing fingernail. The vent communities are metabolizing hydrogen sulfide in darkness. The cold water corals are adding 1 millimeter to their skeletons every few years. The AMOS is slowing at a rate our instruments can now measure. The sediment is accumulating at perhaps 1 centimeter per 1,000 years. The nodules are growing at 1 millimeter per million years. All of it, simultaneously, right now, in the dark. We have mapped less than a quarter of it in detail. We have sampled a fraction of the species living in it. We have drilled through perhaps a thin scratch of its sediment archive. We have deployed sustained instruments on a handful of locations across an ocean basin covering 1/5 of the planet's surface. And every time we send something down, every time an ROV descends through the lightless water column and its cameras resolve the seafloor below, something appears that wasn't in the catalogue. A new morphology, a new community, a new chemical signature that requires a new explanation. The floor of the Atlantic is not a solved problem waiting for better technology to confirm the details. It is an open question, actively generating new questions every time someone with the right instruments gets close enough to look. What you see on the surface, the grey Atlantic in winter, the deep blue in summer, the white-capped ocean that Columbus crossed and the Titanic sank into, and the first transatlantic cables once lay beneath, is the ceiling of a world we have barely entered. Below those waves, the ridge breathes, the vents billow, the siphonophores drift in the dark. The sediment accumulates, layer by layer, recording everything.
And somewhere on the eastern flank of the mid-Atlantic ridge, in an area where no research vessel has yet conducted a detailed survey, features sit quietly in an old data set. Mapped once, flagged for follow-up, never revisited. Still unclassified. Still waiting. The Atlantic doesn't give up its inventory easily. It asks for patience, precision, and a tolerance for the discomfort of not knowing. And the deeper you go, the more clearly you understand that not knowing isn't the failure state of science. It's where science actually lives. In the gap between what the instruments show and what the categories can explain. If that's the kind of thinking you want more of, the kind where the answers get strange and the questions get bigger, subscribe and stay with us. The ocean has more to say.